Hello, welcome back to STEM Stream. Today I'm going to show you how you can calculate a sewage pump for a sewage wastewater. So to begin with, designing a sewage pumping station is a critical component in managing wastewater in urban and industrial areas. This process involves various stages of calculation and analysis to ensure that the system operates efficiently and meets the demands of the population it serves. In this example, we will focus on the calculation and the design of a sewage pumping station, which is an essential component in managing wastewater in urban environments. The design process involves determining key factors such as average and peak flow rates, selecting the appropriate pump type and size, calculating the necessary pipe dimensions, and accounting for hydraulic losses. Additionally, the energy consumption calculation are made to ensure that the system operates efficiently and sustainably. This example guides you through each step of the design process from wastewater flow calculation to energy analysis, providing the necessary foundation for building a reliable, energy efficient, and effective sewage pumping station. So you will have some specific data that you will use in order to calculate it. So we will be focusing on designing the pump unit for sewage water without rainwater. So you will have to have the connected number of inhabitants. Here it's usually around 4,100. The specific wastewater production per person, which is 150 liters per day. Also the ground elevation at the station K1 and the inflow bottom elevation in which the water flows through the well, the discharge pipe length, and the discharge outlet elevation. So this is the wastewater flow calculation that you will begin with in the beginning. So you will use the formula of QBD. So it's the Q times the number of connected inhabitants divided by 86400. Q is the specific wastewater production, 150, and then you get the value in liters per second. Then you calculate the maximum flow rate of non-rainwater wastewater Qmax. This is the one that we will use for the design of the pump unit. So it's the QBD times the Qmax. This is basically a coefficient ratio value, which is 2.1. So you will multiply it by 7.12 to get 14.95. Then you get the minimum flow rate of non-storm wastewater, which is 4.27. Then you calculate the total wastewater production per day, which is 615 meter cubed per day. After you get these values, you can easily now choose the type of the pump design that you would like. So in this example, we will use two submersible pumps working alternatively. Then they also have a guide rail system for easy installation, removal, and maintenance. The features of this pump would be an open channel impeller, so it has a solid handlings up to 100 millimeters. We chose this pump because it's basically the most convenient one for wastewater because it contains a lot of solids, and the open channel impeller power consumption is approximately 2 to 3 times lower compared to a crushing pump. So the focus is on high reliability and energy efficiency in here. Then we calculate the accumulation chamber design, which is the design of the storage chamber volume of the pumping station. So the volume of the accumulation chamber, it depends on the maximum number of pumps switching per hour, which is specified by the pump manufacturer. So if we chose the number of switch-ons per hour to be 5, some manufacturers can give higher values, which is up to 16 switch-ons for a pump power, which is up to 35. Then the minimum pumping time will be 60/5, so it's 12 minutes, which is zero point 0.2 hours. For the operational requirements, you have the maximum ones is 5 starts per hour, and the minimum pumping time is 12 minutes. So the minimum required volume of the storage chamber of this pumping station will be the T minimum times the Qmax over 4. Then you will get this value. So for the construction of the pumping station, we will use basically here prefabricated well frames with an internal diameter of 1500 millimeter. Then you can easily calculate the required height between the switching on and the switching off level in the pumping station, which is 4V minimum divided by pi d squared. So you plug in the values and you'd get 1.52 over meters. So this is how the figure looks like. So you will also propose a set level below the bottom of the tributary. It's usually 200 millimeters here proposed. So the tributary, it is the inlet pipe where the sewage flow into the well, into the wet well. The bottom of the tributary is the invert level of that inlet pipe. It is the lowest inside the surface. So setting the water level 200 millimeter below ensures that the sewage does not back up into the pipe. So it prevents basically a reverse flow and also keeps a slope for smooth flow into the pumping station. So the first level here you'll have to calculate is the switch on level, which is right here. You also have to know that the switch off level and also the alarm level. So these are the three levels: the switch off level, the switch on levels, and the alarm level. So to calculate the switch on level, you will have to use the 317 minus 0.20, which is this 200 millimeters, to get your switch on level. Then you will calculate your switch off level, which is right here. So it's 316 minus 1.52. The 1.52 here is the difference between the switch on and the switch off levels, which ensures that the pump does not cycle on the 1.5 on and off too frequently. And the distance helps avoid short cycling, which can cause wear on the pump and reduce its efficiency. So the idea here is that the pump will only activate when the water level is sufficiently high and will shut off once the water level has been sufficiently reduced. Then you will also have the alarm level, which is 316.9 meters, and it is the level at which the alarm is triggered. So to alert the operator to a failure of the pumping station, it is proposed to be 100 millimeter below the bottom of the tributary. So it is 317 minus 0.10, which is 316. Now you write down all of these values into your figure and you can easily see that this is your switch off level, switch on level, and your alarm level. Then you will calculate your discharge pipe design, which is the fourth step. So to calculate it, we'll use the continuity equation, which is area times the velocity. We know that the area of any pipe, it's pi d squared over 4. So you would rearrange it to have your pipe diameter as the value here. So you will have 2 square root q max over pi times VV. You will use your VV is equal to 1.0. It is the velocity of the pumped liquid in the discharge pipe according to the EU Slovak standard right here, which shall be at least 1.0 with a minimum pipe diameter of the N100. So if the pipe is secured against blockage, the use of the crushing pipes, then the pipe diameter should be smaller. So then when you calculate your diameter here, so you will plug in all of your values, you get the diameter 0.138. You'll use the tables from the EU code to choose the most um, close diameter from the tables. And here we chose 125 because the bigger one, it's a lot bigger. And this one works much more better. So we chose this one because it's close to the value that we computed. Then you can easily calculate the actual speed depending on the continuity equation, which is 4q divided by pi d squared. So you plug in the values, you get your velocity 1.22 meters per second. Then the fifth step here to calculate the pump unit for the sewage wastewater, we calculate the hydraulic losses. So hydraulic losses, they are the values for the loss heights that are calculated basically according to the Darcy-Weisbach equation, which is the v squared over 2g and then pi l over d plus the sum of the losses here. So we are considering the design of the sewage pump system, which includes like fittings like bends, valves, and connections. So we will continue the calculation and use this formula right here to calculate the local head losses due to the pipe fittings. So there's also another method which is called the equivalent of length replacement of length method. So we chose this method right here because it does make much more sense. I do prefer it because it has the Darcy-Weisbach equations and much more kind of better, easier principles to apply. So you convert the flow rate to cubic meters per second using the Qmax value, which is in meter cubed per second, divided by 1000. Then you calculate the velocity in the pipe using this equation pi d squared over 4. So pi times 0.125 over 4. So which is 0.01227. Now you calculate the velocity in the pipe, which is q over a, which is 1.22. Then you calculate the local loss coefficients. So let's assume the following local loss coefficients for the system components. So for a bend, it's 0.5 times the bend, which is 0.5. For a valve, it is 1.5. Then you calculate the head losses due to fittings. So now we apply the equation for local head losses for the bend. So it is H bend, which is the minor losses of the bend, V squared over 2G. So it's 0.5 times 1.22 squared over 2 times 9.81, which is 0.0317. And for the valve, you calculated also another step for the valve, which is the minor loss for the valve, V squared over 2G. And then you calculate the total head losses due to local losses. So you basically add both losses computed. And then you have the total head losses here is 0.1268 meters. To calculate the total head loss equation, after we have already the local head losses, we can combine them with other components of head losses, such as the Juditech head loss and also the friction losses. So to calculate the Juditech head calculation, we use this formula right here. So this is the vertical distance between the pump inlet and the discharge elevation K3. And you plug in all of the elevation levels divided by 2 to get this value. Then you calculate the friction losses using also the Darcy-Weisbach equation right here. And the total friction head loss can be calculated. You need to first of all calculate your Reynolds number. So it's V times Z divided by kinematic viscosity, which is 1.22 times 0.25 divided by 1 times 10 to the power of minus 6. Then you calculate the friction factor F using the Kohlberg-White equation for turbulent flow. So the friction factor can be approximated using this value, 0.079, divided by the Reynolds number to the power of 0.29. So it is 0.079 divided by 152.500 to the power of 0.25, which is 0.19. Now we substitute these values into the Darcy-Weisbach equation right here to get your value, which is 1.47. Now you calculate the local head loss, so previously calculated in the head loss equation, which is 0.1268 meters. So this is the total head calculation. You sum up all of the values to get the value, which is 18.0568. Then you calculate the pump selection parameters. So based on the total head, you have the 18.06, which is the overall values, and the design flow rate 14.95. We select a suitable pump from here. So the pump type here, you have certain pumps from the catalog. Here I used the Fleet catalog. In the pump catalog, you can also see the performance curves. Each curve shows the flow Q values, usually on the horizontal axis, and usually on the vertical axis, you have your head calculated for each pump. So the motor power will depend on the efficiency of the pump and the energy required to overcome the total head at a specified flow rate. So this is the head, this is the flow. And from here, you have different types of pumps. So based on the parameters that I calculated, we can see that the HT is the most suitable value because you have your flow value equal to 14 and your total head is equal to 18. So if you go here, they both kind of collide into the HT pump model. So this is the pump model with an impeller of 481, and it should be a good candidate because it should be checked against also the performance curve to ensure it operates efficiently as required. So the choice of the pump type is according to the input power, is in terms of the connection of the pumping station to the power grid, but it doesn't have a significant impact on the overall energy consumption. So, I mean, overall, the pump type unit can be shown here is the HT pump model. Of course, there is a lot of other pump models, like for example, the Grundoffs and also other models, but I use this pump model, the Fleet one, because it is the most commonly used for sewage wastewater pump units. And this is basically also all of the characteristics for the model you can also see from the catalog, such as the vortex, the grinder, the discharge size, the power rating, and so on and so forth. And this is how it looks like, and some also further details about this pump model type. All right, so that's it. This is how you can actually calculate your sewage pump model. I hope that it helped. In case you do have any questions, feel free to write it down in the comments, and also like and subscribe to this channel. I would greatly appreciate it. Also, STEM kind of offers a lot of other courses related to water management, so in case you would like to look at them, feel free to check them out. And as always, I'm rooting for you.